Let's consider now the two equations that we know for the evolution of the universe, the Friedman equation and the fluid equation. You see that the second term in the Friedman equation is proportional to the density times the square of the scale factor, whereas what is in the left-hand side of the fluid equation is the time derivative of the cube of the scale factor times the density. So if we multiply the Friedman equation by the scale factor and take the time derivative, then we can relate to the Friedman equation in the fluid equation. So let's do that. Let's multiply the Friedman equation by A, and now take the time derivative. The time derivative of this becomes, so you see already why we're heading towards something that should be called acceleration equation, because we now have an A dot dot term, that's the acceleration. Now the second term, you take the time derivative and you have the term that appears in the fluid equation, rho A cubed. Now if we substitute the fluid equation, now if we substitute this dA cubed dt by 3a squared A dot, then this becomes, so we can eliminate the A dot on all terms. This cube becomes square, and this is the equation that I have in the end. Now, the left-hand side of this is different than the Friedman equation, but you can see that the right-hand side is the same. So in fact, this must be identical to the left-hand side of the Friedman equation. So let's substitute the kc squared as given by the Friedman equation. And we can immediately see that we're gonna cut the A dot squared term. We can eliminate now the remaining scale factor in all of the terms, divide all the sides by 2, and you have an equation for the acceleration. So this is the acceleration equation. We can see from this equation that pressure slows down the expansion. If the pressure is bigger than 0, positive pressure, then you have that the acceleration is negative. Now, this is counterintuitive because from kinetic theory of gases, we are used to pressure making things expand. In fact, this notion does not apply in cosmology. In usual fluid mechanics, it is the pressure gradient that enters in the momentum equation. In cosmology, there is no pressure gradient to exert force because inner and outer pressures are the same in the shell. What is happening here is that due to energy mass equivalency, the gravity of the fluid's kinetic energy is providing the slowdown. That's why a positive pressure leads to a deceleration. Now, this equation also shows a way to have a positive acceleration. You either would have negative density, which is non-physical, or you would have a negative pressure. Negative pressure, if there is a fluid that exerts negative pressure, this fluid would lead to a positive acceleration. So we see here how we can interpret the observation that the universe is accelerating. That would be the case if there is a component in the universe that we have been ignoring that has negative pressure.